Hi everyone, and welcome to the Chapter 10 lecture on t-tests for independent samples. Before, we talked about t-tests for a single sample, where only one mean was compared to a specific number, typically a population. Now, we're going to talk about a t-test for independent measures, which is a research design that uses a separate sample for each treatment condition or each population. In other words, we have two groups that are completely separate with different people and sometimes different sample sizes. We also call this a between subjects design, so you might see that thrown around as well. Independent measures designs are more commonly found in true research as opposed to the single sample, because as you know, we don't typically have population information. Rather, our job as researchers is more often to learn about a population by taking a sample. Before jumping into the math, I think it would be helpful to talk about what kind of questions we can answer with an independent samples t-test. We might ask, does a new medication significantly reduce depression compared to a placebo? One group gets the medication of interest, and the other group gets the placebo, which might be a sugar pill that does not have an effect on depression. In this example, there are two different or independent groups. Then, with a t-test, we can compare the means to see if they significantly differ. We might also ask a question like, is there a difference in self-reported happiness between men and women? You could give a happiness questionnaire to each distinct group, then compare the means and see if those groups significantly differ from one another. For this class, we're going to use formulas from another book. While the different formulas accomplish the same thing, I find that the ones shown in this lecture are typically easier to understand and don't use sum of squares, which is not a frequently given number or statistic. The equation is the mean of group 1 minus the mean of group 2 divided by the estimated standard error. The estimated standard error is notated as S sub difference because we are looking at mean differences. This estimated standard error is an estimate of how well the sample mean difference reflects the population mean difference. In other words, is the difference between our means similar to what we would expect to find in the population? Because we have two means, we calculate the estimated standard error a little differently. There are 4 steps to finding the estimated standard error for an independent t-test. First, we need to find the total degrees of freedom. Next, we need to find the variances for each sample if it's not provided for us. After that, we find the pooled variances, which means we're combining the variances from each group. And lastly, we use degrees of freedom and pooled variance to solve for the estimated standard error. We calculate total degrees of freedom by adding the degrees of freedom for group 1 plus the degrees of freedom for group 2. And if you remember from the last lecture, when we have a single group we are running a t-test for, the degrees of freedom is just n minus 1. So we just subtract 1 from both groups and then add them together. So if we had two groups, one with 25 people and one with 20 people, the degrees of freedom for group 1 is 24 and the degrees of freedom for group 2 is 19. 24 plus 19 is 43. Once you have the total degrees of freedom, you can find the pooled variance, which again is just combining the variances of each group. In this lecture, the variances will be given to you, but you can always review the Chapter 4 lecture if you need a refresher on how to calculate this. The equation for pooled variance is degrees of freedom for group 1 divided by the total degrees of freedom multiplied by the variance for group 1 plus the degrees of freedom for group 2 divided by the total degrees of freedom multiplied by the variance for group 2. We'll have practice with this later on when we combine the steps. And finally, with these steps completed, we can solve for the estimated standard error, which again we call S sub difference. The estimated standard error is the square root of the pooled variance divided by the sample size of group 1 plus the pooled variance divided by the sample size of group 2. So conceptually, we have the same standard error equation from before, but this time we're calculating the error for two groups together. There is one last thing we need to do before we solve for t, and that is check the assumptions of the test. For an independent t-test, the observations must be independent. In other words, we have two distinct and non-overlapping groups. The data for both groups are normally distributed, and the samples must have approximately equal variances. We call this homogeneity of variance. Essentially, if the variances of the groups are wildly different, it increases our chance of type 1 or type 2 error. To find whether or not the variances are roughly equal, we run what's called an F-max test, which is just dividing the largest variance by the smallest variance. For instance, say we have one group with a variance of 4 and another with a variance of 9. We divide 9 by 4, and that gives us 2.25. From here, we need to compare this to the F-max table to see if the table we have falls into an acceptable range. You can find this table on Canvas in the Stats Tables folder. This table is read a little differently than others in this course. We're sticking to the standard 0.05 p-value, which means we are only looking at the light face type. Ignore anything bolded. In the left column, you'll see n-1, and this is assuming that the sample sizes in each group are equal. If there's different sample sizes with each group, go with the smaller sample size because that allows for a more cautious estimate. Then we have k, which is our number of samples. With a t-test, we are comparing two groups, so we use the 2 column. With that, let's use that example of an F-max of 2.25. Say there are 7 people in each group. n-1 is 6, so our critical value is 5.82. Our number is smaller, but that is a good thing in this case. If the number is statistically significant, it violates our assumption. We want that number to be lower than the critical value. Therefore, our F of 2.25 suggests that our variances are relatively equal, and we can go ahead and run our t-test. With that, let's put all of the steps together. Say we're interested in whether high school students differ from college students on time management skills. We'll use HS to stand for high school and C to stand for college. So using the statistics provided, let's state our hypotheses. You'll notice that we are only interested in whether or not these groups differ, so we have a two-tailed test. But before we run the test, we have to make sure our data meets assumptions. These groups are independent because they consist of two different groups of people with no overlap. For this class, you can assume normality. Then we need to check whether the variances are equal. Using the F-max test, we have 1.6 divided by 0.9, which is 1.778. Checking this with the F-max table, our criteria is P, which is notated as alpha, is 0.05. Our degrees of freedom is 19. However, this number is not listed in the table, so we go to the next smaller number. So our critical value is 2.86. 1.778 is less than 2.86, so we can proceed with the test. From here, we can set the criteria for the t-test. We use the same t-table as before, but we use the total degrees of freedom to find the critical value. So setting our alpha to 0.05, our total degrees of freedom is 38, which again we get by adding the degrees of freedom for both groups, and that makes our critical value 2.042. From here, we can find the estimated standard error, but to do so, we need to find the pooled variance first. Plugging in our degrees of freedom for both groups, the total degrees of freedom and then the variance of the groups, which was given to us on the last slide, we get 1.25. We can then plug that in to the estimated standard error equation, which gives us about 0.354. And now we can solve for t. So using the t equation, we subtract the mean of group 1 and the mean of group 2 and divide by the standard error, which gives us negative 5.08. You'll notice that this is notated as t with the total degrees of freedom in parentheses equals negative 5.08. You should write your answers in this format because this is the notation used in research articles. Next, remember that we always look at the absolute value of the result. So comparing that to the critical value, 5.08 is greater than 2.042. So we reject the null. There is a difference between high school students and college students' time management skills. Here's a problem for you to solve on your own. The question is, do participants perform differently on a test in noisy environments compared to quiet environments? Pause to solve. The answer will be shown in 5 seconds. So first things first, can we run the test? The groups are independent, we can assume normality, and setting the Fmax criteria, our critical value is 9.6. The Fmax is 1.88, so we can proceed. We set the t-test criteria. This is a two-tailed test, and the critical value is 2.365. Finding the standard error, our pooled variance is about 3.443, which makes our standard error about 1.245. Then solving for t, this gives us 3.212. So comparing this to our critical value, we can reject the null. There is a difference between taking a test in a noisy environment versus a quiet environment. Lastly, we can find the effect size. The estimated Cohen's d can be found with the equation mean 1 minus mean 2 divided by the square root of the pooled variance. You can pause to solve for both examples if you would like, but I'll continue here with the answers. For the management example, we have 5.6 minus 7.4 divided by the square root of 1.25. Which is roughly negative 1.61. Using the absolute value of this number and pulling up the table from last lecture, this is a small effect size. For the testing example, we have 21 minus 17 divided by the square root of 3.443, which gives us about 2.16, which is also relatively small. And that is all I have for you. Please let me know if you have any questions.